And I just now remembered to hit record, so we're on problem dose, and I'm sorry for people watching the recording. We are practicing analyzing forms of energy, problem statement is on the board. I'm giving people a little time to reflect. So again, question is, if I drop a ball from a height, the instant after it leaves my hand, instant before it hits the ground, what form of energy do we start with? What form of energy do we end with? Form or forms? Are there any unaccounted forces doing work? If you're moving at 9.8 meters per second, do you have kinetic energy? If your velocity is 0, do you have kinetic energy? There's still a number of inconsistent answers in here. Please reflect on this. Either you've got kinetic energy or you don't. If you have an initial velocity, then it also logically follows that you must have an initial kinetic energy. If your initial velocity is 0, you can't also have kinetic energy. Please go back in and change either question F, your initial forms of energy, or question I, your initial velocities. There should be consistency, at least, between your answers. Okay, time's up. What's the equation for velocity in terms of acceleration? Velocity equals, in terms of acceleration, initial velocity plus what? How do you find a final velocity? Initial plus AT. Initial plus AT. What's the acceleration in free fall? G downward, right? What is your speed after 1 second of fall? Or what is your velocity after 1 second of fall? If t equals 1, after 1 second of free fall, how fast are you going? 9.8 meters per second. How fast are you going after no seconds have elapsed? 9.8 is not the speed of free fall. 9.8 meters per second squared is the acceleration of free fall. And if that acceleration has no time to build up motion, the instant you release a ball, it does not spring into a constant speed motion. It has to speed up faster and faster. So the correct answer for the follow-up question I was 0. The instant you release something, it is at that instant not moving. Gravitational weight force has had no time to accelerate it. Write that down as a note. If you said that the initial velocity is 9.8 meters per second, or that the velocity is 9.8 meters per second squared, take a note to yourself. The instant after something is released, it is not moving. Velocity is 0. Okay, if that is why you said that there is initial kinetic energy, congratulations, you are internally consistent. Hopefully now you realize if velocity is 0, mv squared, half mv squared is also 0. I'm still mystified. There are a number of people who are telling me that there's kinetic energy when there's zero velocity. Remember, kinetic energy is motion energy. If you have no velocity, you can't have motion energy. Okay. Or maybe you're just not paying attention and just randomly key mashing. I don't know. Okay. Initial forms of energy. Let's go down the checklist. Do you have motion energy the instant you're released? No, I just went into that. Do you have height energy? Yes, you're up. You're going down, right? You're decreasing in position. Have I said anything whatsoever to lead into thinking that there's friction or that that's going to be calculatable? So the initial forms of energy is just UG. Okay, let me scan here on final energies. Better, but still worth practicing. The instant before it strikes the ground, is it up? On the ground? How high are you on the ground? I'd say you're at height 0. Is there potential, gravitational potential? No, if your height is 0, mg times height is 0. Is there kinetic energy the moment before you strike the ground? Are things moving just before they hit your foot? You betcha. Okay, so what form of energy must you include? And have I said absolutely anything about thermal? So it's just kinetic at the end. What forces act on the ball as it falls? Well, forces are acting on a freely falling object. Wait for what? Huh? What else? Trick question. There is nothing else. There's nothing else attached to a freely falling object by definition of freely falling. Yeah, if you want to be super precise, maybe there's a drag force, but specifically, I said, unless I specifically say something specifically about this, the situation of having drag, we're always going to ignore it. Drag equations are nasty. Weight force is none. Follow-up question, follow-up to the follow-up to the follow-up. No, this isn't a follow-up to the follow-up. Question J, can you write me the statement of conservation of energy? I've written down what I start with, what I end with, and what I change by. Can you come up with an equation that relates these three quantities? What do I do to energy initial, energy final, and work? What is the equation which links them? Plug in what kind you got. Does that make sense? You see what I'm fishing for? Smell what I'm stepping in? State the law of conservation of energy, plugging in the appropriate forms in the appropriate places. And for this problem, plug in what you know about the forms. So just tell me E final equals the initial, blah, 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 blah. What kind of E is the final? Okay. May I have your attention for a second? A whole bunch of people are telling me correctly, change in energy is work. That's a true statement. But just like when we were doing force problems, F equals ma is true, but just writing down F equals ma doesn't answer the question, apply this to the particular problem. It would be tension minus weight equals ma. I want you to tell me what is the change in what forms of energies? What value of work would we plug in? There are multiple ways to write this equation, by the way. There's more than one right way to factor this. I want you to plug in what you know about this. There's more than one way to write this. Actually, Alex told me that she thought that people would be more comfortable with saying you end with what you started with plus what you got. Final equals initial plus change. You can also write change equals external work. Now, if we plug in what each symbol got, what is the F? Kinetic. In particular, I would say final kinetic to distinguish it. What is the I? In particular, I'd say initial potential. What is the work done? You don't have to write the plus zero. Anything plus zero is itself. Change in energy. Perhaps you think of it more naturally, and change in energy equals what you done did. What's the final minus what's the initial? What's the work done? Either of these are correct answers to what, or what I was looking for J. Does that make more sense? We've built up the pieces of the equation, then you plug into the master equation in either form you like. Okay. By the way, I would like you to reflect on something. What happens if I throw a ball up and it reaches a max height? What forms of energy did I have? Kinetic and potential. When a ball falls from a height just before it hits the ground, what forms of energy did I have? Please reflect on this. These are reciprocal processes, saying that kinetic becomes potential, then why do you even, what, I can't do it anymore. I can't. Anyone use Notability who knows why you might not be able to scroll? Screw it. Okay, I just can't even with this. I can't even with this. Okay, I apologize for not being able to get to that slide now. Correct. Yeah, do you know? I will try those arrows. Nope, no dice. Very frustrating. Yeah. Ah, ha 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 ha, that one. That succeeded. Okay, so if something is going up and down in the air, two forms of energy that we got are potential and kinetics. Kinetic becomes potential on the way up. Potential becomes kinetic on the way down. Let me give a different sort of example. A bunny pulls another bunny on a sled at constant speed through the snow. Hey, deja vu, we did that once upon a time, yeah? So KLM are going to be Max pulls Ruby. No, I shouldn't say that. A sled is pulled. I want to focus on the sled. What are we? What did I just say? K, L, M. E, I, E, F, E, I, E, I, O, work. Ready, set, go. We have less time than before. You decide. You decide what makes sense in the context of this problem. Sure. So again, for K, I'm looking for one of three letter combinations: U, G, K, or what is it, TE? For M, I'm looking for the name of a force or forces. I'm sorry. This isn't the problem I originally gave you. This is the follow-up. I'm gonna give you the problem that I first gave you. Speeding up, no friction. Ice is iciest. She's speeding up as she goes along. Yeah, so the first problem here, I'm sorry, not constant speed, constant acceleration. Bunny is running and running faster and faster. The follow-up is going to be follow-up is we're going to be let there be friction. Okay, I think you're either there or not. Who wants another minute? Okay. Again, your choices for K and L, please, are UK and TE. The name of a force is not, doesn't make sense for this. And the answers are, did I say anything about height changing whatsoever? There's no U. Is there any motion going on? You betcha. Is it heating up at all? Not after I said no friction. I'm sorry, did it start with hotness? No. Nor is there going to become hotness at the final time. Okay. What forms do I end with? Is it going uphill? I said nothing about it. There's no final potential. Did I say, is it moving at the end? You betcha. There's more motion. I said constantly acceleration. Actually, I guess it could be slowing down as well. No, I'm going to assume I'm speeding up. Is there anything to indicate that we're developing thermal energy? Specifically said no friction. So moreover, what can you conclude about Ki versus Kf? Why? To be as the problem was stated, you could say, well, actually, it doesn't have to be speeding up, but I won't give you questions to trick you at that level anyway. If I'm saying pulling, accelerating it on a snowy surface, you can guess that I'm saying speeding up. If I'm saying pulled, speeding up by a tension, the tension can't slow you down. There's no friction, there can be no slowing down force anyway. So actually, I take it back on taking it back. This problem, as stated, is precise. What is the only force that does work? Friction? I said no friction. Tension. And I shouldn't say tension, I shouldn't say work equals tension. Force doing work is tension. I never wanted to let W equals T appear on the screen. N, write down conservation of energy equation. What can you conclude? What's the final? What's the follow-up? State the law of conservation of energy, plugging in what you know. Question N, by the way, not O. Okay, and the correct answer here is the change in, I'm going to say final equals initial plus work. Final equals initial plus external work. I should say work done by tension. I'm not going to say T. Tension is a force, work done by tension. Let's actually get into those equations, by the way. Question O, plug in the equations for KF, KI, and work done by tension. Show me if you remember those equations. Don't look at your notes for now. Don't look at your notes. See if you can remember. Try. What is the kinetic formula? What is the work formula? Again, plug in those formulas to this particular example where we have some final, some initial, and some work done. What is the final equation? What is the initial equation? What is the work equation? I didn't say that they started moving. That's what I said in the original problem, didn't I? I said he sped up from blank meters per second to final meters per second. If you put 0 initial kinetic, that's consistent with what I wrote. And if I had accidentally written it this way on a test, you would have gotten points after I realized that I didn't state precisely. Anyway, time's up for this because I want to get one more down. What I would say is the kinetic energy equation, half mv squared, I write as half mass final velocity squared, not 0, half mv initial squared is the initial kinetic energy. Again, if you were thinking as I was, that he was speeding up as he ran across, plus formula for work is force distance cos theta. What's cos theta in this case? Positive 1. So I just say tangent delta x because I know force is in the direction of motion. The tension is pulling the sled, speeding her up. That's what it'd be. That's what you would apply if you were doing this problem in a that's what you would do if you were doing this problem in a if you were doing an energy problem, you would need that equation. What I'm struggling to say. Okay, I get you for a few more minutes. Let's do one more. No, follow-up. Questions. Give me questions. I never get as good questions when I ask out loud. So question P is, tell me where you're struggling. What's easy, what's hard here? Turn to your neighbor and discuss for a second. And then in question P, tell me where you're struggling. Plus, Ryan, I add these things together. MGH, MGY equivalently. Mass times field times height. If you didn't have the formula memorized, that's fine. That's fine. I'd like you to get these. I mean, it's only 5 total formulas. You've met 4 of them. I encourage you to knock them down ASAP, but that's what you're struggling with now, not rotational kinematics. We're not doing that now. We're not doing that. You can take it. Well, I want you to know it, but not today. Ah, there. Here's a good one. Can anyone tell me why we didn't consider the work done by the normal force as the sled was pulled across the ground? It's 90 degrees to displacement. Which way does normal point? Which way does the displacement go? 90-degree angle. Cosine of 90 is 0. And again, if you think about it, think about this for a second. You don't have to memorize this as an equation. Meditate upon this. As I walk along, is the ground helping me speed up or slow down? Is the ground doing absolutely anything to me but keeping me from falling through it? There's a normal force. I'm displacing, but normal force isn't helping me displace at all. And yes, the person who asked that, is it because it did not contribute in the direction of motion? Yes, absolutely. Okay. Again, if you are struggling with memorizing the equations yet, that's okay. What I want to be able to do today, what we're focusing on, what I see a lot of struggles with, is just being able to identify which form or forms of energy do we have, rather than, all right, let's plug them in and solve a problem. We can do that more next time. We have time. Okay, one more. I'm going to identify one part here. And I'm going to say that suppose the person does not take a running leap into the top of the slide. Oh, I don't know about you, but I'm a little nervous on these things. I just drop from the top. I don't usually running start this. What are we at? QRS? I have you until 40. Yeah, 40? 45. Okay. 12 more minutes. Tell me, say that again. Say that again. What do we need to?
That the water slide is moving at the 1.4, and they figure that out and then do gravity.
Which direction do you move along a slide?
Yeah,
Which direction is the normal force? Always perpendicular to the direction of the slide. Doesn't matter whether the slide is going down steep, down shallow. Normal force is defined as being at right angles too.
but we don't need to sign them because for
Normal does no work.
I think I'm forgetting signs only for normal.
You're talking about force, distance, cos theta? Wait, I think I misunderstood the question.
For like angle on a slope, find out how this velocity. The question is asking what speed you exit the slide.
You can do this without the acceleration formula. Do this strictly considering energy.
I have a question. So gravity pulls you down
Uh-huh.
on a flat surface, it's equal to the normal force pushing back out.
If we're not accelerating, yeah, sure.
But if I'm on incline, gravity's pulling me straight down still, but a normal force is it still equal?
Part of weight presses you against the surface. Part of you points along. A force straight down can be said to be equivalent to a little force in and a little force along. That's a subject that we skipped over. That's
Okay.
the subject vector, how to decompose a vector. You want to understand why acceleration is g sine theta? We have to go into that. But that was too triggy
Is that just like
for us.
a squared, a b squared?
It does. Actually, so, and there's sine and cosine, opposite over hypotenuse, adjacent over hypotenuse. Better. The vast majority of you correctly said you start up. You start with potential energy. That's correct. I would say there's a UGI here. Now read carefully. Do I end with a height? Read carefully. I'm going down, sure, those potential energies are not going, gravitational potential energies will be different, but I did not say I go to height 0. I said 3.2 meters above the bottom, 1.4 meters above the pool. Yeah. Did I say anything about friction causing thermal? Wait, I said no friction. Okay, any forces that do work? Can I get people saying wait? Okay. Just one. Okay, again, if you said wait, if you said wait, the thing to know is that if you're already doing potential, gravitational potential, considering weight is double counting. Don't do that. You can't do that. So we don't need to include a weight. No forces do work in this. Question. Potential energy doesn't care about direction of motion. Potential energy only cares about what height you're at. Which way I'm going is absolutely irrelevant. If you're moving horizontally, that's going to say at that instant, you're not changing your potential energy. But what is the value of your potential energy? It's not 0. It's whatever mg times your height is. Good question. Others? Okay, I've got you for 7 more minutes. One more. No, not this one. I have a box sliding along a plane. I'd never give you this in forced land. I can ask you, and I won't give you this on the homeworks or the tests to solve with this. But this is totally valid for me asking you about what form or forms of energy they'd be. Okay, so I kick a box uphill on a wedge with some angle. I give it some V initial. You don't need to know all the letters. I'm just asking you to identify the form or forms of energy. So from the instant it starts up the wedge, and it's a rough surface, it's friction. It goes up the wedge until at some actual height, static friction takes over, and it comes to a rest. Okay? At the peak of its motion, it comes to rest. I will also give you the hint that considering thermal energy and work by friction is double counting it. Don't tell me that there's both a thermal and a work done by friction. Let me just say, for the sake of uniformity, if there's a work done by friction, don't tell me thermal. There is no final thermal. I'm going to ignore thermal. We're just going to talk about it as a freaking work. Okay? TUV, EI, EIO, EF, and forces that do work. Hint, hint, hint. One more time, the hint I just said is thermal and friction work, two sides of the same coin. Don't include it as thermal energy if there's something going on there. You'd have to be told one more thing. But whatever potential, whatever height is, it's gone up. There's some height. You've moved along the ramp. What I might give in a class that included trig is I'd say if you go a distance d, that's the length of a hypotenuse, d cos d sine theta would be this distance. Maybe, sure, yeah, yeah. Oh my God, please listen. Hint for final energy. Thermal energy and work done by friction are two sides of the same coin. Don't include them both. If there is one of these, I encourage you put it in the work column. It's not wrong the other way, but listen to directions. All right. Much better than when we started. Initial, is it moving? Is it up? And I gave you a hint, there's no initial thermal energy. Initial energy is just K initial. Final energy, is it moving? Not as I described. Is it up? Is it hot? Yes, but I said don't include it there, because that'd be double counting if you include thermal and internal heat. Force that do work. Friction. And I don't think anyone said wait. Great. We're going to pick up on this. We're going to be applying this and plugging in equations next time. But it is end of class. Adios.